Welcome back to my open learning session where I'm going to catch up with deep learning using this book called Mathematics of Machine Learning. It is an open MIT book. The link is in the description. So today we are going to look at transformations. It is 2.32. Yeah, elementary transformations. Key to solving system of linear equations are elementary transformations that keep the solution set the same, but that transformation the equation system into a simpler form. But that transform the equation into a simpler form. So what that means is we take something like that and we make it simpler. So we have three rules: exchange of two equations. So we can take any of those equations and we can exchange them. The second rule is multiplication of an equation with a constant which is not zero. Because if you multiply by zero, then it's always zero. So that's not allowed. But what we can do is we can just scale up or down the equation. Also, what we can do, we can add. What we also can do is we can do addition of two equations. So we can add one equation to another. Okay, they gave us here an example, 2.6. For a element of the real number set, we seek all solutions of the following system of equations. Okay, so let's first check what we have. I can see that we have 5 variable x here on the left side, right? 1, 2, 3, 4, and 5. I can see that we have on the constant side something called a. And they mean a, what they mean with a is basically it is a number. In the end, it's not something we want to have it be able to change, but we just don't know it. So we can think of it like 5 or 6 or so, just a normal number, but it's we just have the difficulty that's unknown. Okay, so the first step is to convert this into the augmented matrix. This is what we have here as the augmented matrix, and this is just in my view, it's just a lazy way to write it, which is, I think, good. We have the coefficients of the variables on the left side, and we have the constants on the right side. And what they do is they have rows now. Basically, they call it row 1, 2, 3, and 4. And what they do here is they swap. Here they swap row 1 with row 3. Okay, so here now we have them already swapped. So if we take a look at our first row, this one, we will find it now, it's on the third place. The next step is, so let's go one step back. They could swap it because our first rule is telling us, let's call it 1. 1 is telling us that we can exchange two equations. And this is what they're doing. They're exchanging the equation. And before maybe we go to the next step, let's try to figure out what we actually want. In the end, we want something like this, I don't know, stair version of the equation. We want to have as many nulls on the bottom left side. So basically, this is the whole point. What we're doing is to move the nulls down and to the left. Okay, so the second step now here is they do addition. They say they add to the second row minus 4 R1, and then to the third row plus 2 R1, and to the third one minus R1. Okay, you can see that I think like the reason is that we have here, for example, the 4. It's like a good match. Also, it's a good match here, right? That means that because we have the same ratio in both, that just of this one operation, we can get 2 nulls here. This is the whole point. Let's get 2 nulls first. And the second part is basically the same, just that here they can get 3 nulls. And the last point is even better. Here they get 4 nulls. Oh no, sorry, they get 2 nulls. Okay, so this is like a progress. What they do now is, I'm not sure if this is the rule which is been written here, but once you have touched one row here, usually you do not want to touch it again. So that's why they do all the they take the first row, then they add it to the other rows, if it makes sense, and then they will not touch R1 again. This will somehow mess up the system of linear equations. So for example, if you now try to do something with R3, and then later on you do something with R1 again, then I guess it messes up. So they will not touch R1 again. But what they can do now is touch the other ones, R2 and R3. So in here, they actually do it in the same time. And we are just talking about addition. So here, this part. Okay, so what they do here is now they take minus R2 and minus R3. And because we have nulls here anyway, it does not change anything in the first coefficients. Minus R2 and minus R3 of those two. And one of those is 0, so you do minus 1 plus 1, which makes 0. And then the second one is the same thing, so you will have these two being 0. Okay, actually it's another one. Didn't saw that. Wow, the whole row is 0. Okay, now what we have is basically almost the right form, but we just want to scale it up and down. So first they flip the sign here, just to make a plus here and here. I'm not sure why, but maybe it's just nicer. And this one makes sense. You can divide by 3. Usually if you can divide by some kind of a prime number, it's a good thing because you make the numbers more primitive. And in the end, we have that equation here on the bottom. Yeah, this equation. Okay, let's go to the next text. This augmented matrix is a convenient form for row echelon form, reverting the compact notation back into the explicit notation with the variables we obtain. So we obtain this system of equations. Okay, and the next part, which is quite interesting, is that only for a equals minus 1, this system can be solved. Okay, so why is that? We know that this system is true as a whole or not. Like it contradicts, like in mathematics, you can basically say anything you want as long as you don't contradict yourself. That's like the whole point of math, right? If this is true, then you could do that. And if that would be true, you could do that. But you could not arrive to a point in like an endless if else case or if and then case where you have like, oh, this number is 2 and at the same time is 4. Like you cannot contradict yourself. So because this is like basically the foundation of all, what they say is only for a equals -1 the system can be solved. Because in our last row we have 0 equals a plus 1. We do not really know a, but we just assume it's a constant, which we do not know. And it can only be 0 if a is -1. Okay, so the next part is finding a particular solution. And a particular solution means like just give me the first best solution you can find. And yeah, you can like try to work it out, but I think what they do is they just are lazy. They say, all right, x5 can be 0 because it's like on every row. Let's assume it's 0, which means that this is all does not count, does not matter really. Then we know that 4 has to be 1. 4 has to be 1. Here 1. And if 4 is 1, we can replace that with 1s. Then we know that x3 has to be -1 because there's no other way. You're like I'm in this row. If x4 is 1, then you have x3 -1 equals -2. So only if x3 is -1, this equation would be true. So that's why they say x3 is -1. Now you have x1 and x2 left. This is the equation you have in the end. x1 minus 2x2 minus 2 equals 2. So you have something like this. Let's move this away. So this is the last equation, which is a bit more complicated because you cannot just say. We have two variables here. And what they say is, okay, in that case, let's just assume that x2 is 0 as well. So this whole part will be 0, which means that x1 has to be 2. And this is exactly the solution we have here. So they have not, so when they are talking about the particular solution, they have not calculated the solution. They have just put zeros when it was a bit complicated in the variables and then just read out whatever made sense and put it into this solution. And having a particular solution is really great because if we go up, we know that the general approach we follow consists of the following 3 steps. First, find a particular solution, which we have. Then find all solutions and then combine. So the particular solution is here. Now the general solution, which captures the set of all possible solutions, is. Okay. Now this is a bit more complicated. They say our solution is vector x, here, this one. And they take our particular solution. I will just put it in green. Okay, they say our particular solution plus some kind of vector plus another vector. Okay, so we have 2 vectors, vector 1 and vector 2. Okay, so the general solution is not being shown how it's obtained, but we can try to think and figure out like why this makes sense or maybe come close to it. We will see a solution called Gaussian elimination, or like a method called the Gaussian elimination, which basically gives us the general solution. But before we do that, let's first take a look here. What you can see is that like First, let's try to understand what's happening. When we are talking about a solution, we mean that we want to know which vectors x, this is a set of vectors, it's not one. Just like basically how many of those different vectors we can put into this equation, and we will get this solution here on the right side. Well, okay. I think not this one. Let's go to the top again. Here. We want to know which vector we can plug in. And we can always only plug in one vector. Or if you just want to see, look at the augmented matrix here, you will have something like matrix A times a vector x equals b. So we're looking for a single vector which is true, but it's like, it's not always one vector. There are many vectors, a set of vectors, but if you read this form here, this one, this is x. This is one vector. So do not be confused that you will see different vectors. You see one vector here and one vector here and one vector here. They are all added together into one vector. So we're still talking about a single vector, which has these properties, and every vector which fits into this description is a solution. So, okay, let's try to figure out again what's happening. In the end, we have a solution which is four-dimensional. Let's try to visualize it. Okay, let's try to visualize it. We have a four-dimensional point. Okay, now we have a problem. We cannot draw four-dimensional. It's even hard to draw a three-dimensional. Let's just do two-dimension. But in our head, it is still this four-dimensional point because I do not want to change the point here. Let's write the equation down. A times x equals b. So let's say this is our b. And this is our particular solution x. A is a transformation. So you can think of A is moving that point, that vector, into this other vector. What you do with matrix multiplication usually, like rotation or transitions and stuff like that. Or you can think of A is transforming space, like all the points in that plane. Does not matter that much. But what we really have here is that that x, it's not only one x, there could be like many x's. And each of those x's, they go, and once we apply the same transformation, they all go to the same point. This is the whole like, let me just copy the equation. Okay, here I copied the equation. So let's think what's happening. We have our x. Now it's green here. That's not good. So this one is actually yellow. Not only is that yellow, but all of those are yellow. So these are our x's, and we have our b here. This is our b. As you can see on the left side, there are many points which will, once we do the matrix multiplication, will go to b. And this description on the right is a description for all those points. So we start with a particular solution. Let's call it P. We start with P. P is here, for example. And we say you can get the x if you add these two vectors to P for a particular solution. We know that if lambda and lambda 1 and 2, there have to be like numbers of a real set. We just scale them up and down. So maybe it's not like, does not make totally sense from what I've drawn here, but what I want to say is you do basically one addition and then another addition. So lambda 1 and 2, then you do for a different number, again 2 additions, lambda 1 and 2. Then you do here lambda 1, lambda 2, and you will always arrive to one of those x points. And not only that, but in case lambda 1 and 2 is 0, you will just stay where p is. I think this is like quite important to understand that we start with our particular solution, which is also a solution, and then we add these two vectors. Now the question is, why these two vectors? And my guess is that because we had 2 times these cases where we had still a variable left while we're trying to reduce it. So in the first case was here. Then we just said, okay, let's do a 0 for x5. But you could find like different solutions for it. And the last part was here, where we just said, okay, let's just put it 0 for x2. And if you take a look, then these numbers, they make kind of sense. And these numbers, yeah, but I'm not totally sure about how to arrive to the particular, to the general solution. Let's just keep it like that, and then we just move on. Okay, let's read the text. In the following, we will detail a constructive way to obtain a particular and general solution of a set of linear equations. Yes, that's what we are needing. Remark, pivots and staircase structure. The leading coefficient of a row, first non-zero number from the left, is called the pivot and is always strictly to the right of the pivot of the row above it. Therefore, any equation system in row echelon form always has a staircase structure. Yeah, that's what we already saw. So what they actually mean is, okay, so that's why they actually multiply it by, or flip the sign. So what they want is this, and they're saying this is the pivot, this is the pivot, and this is the pivot. I think here we only have 3 pivots. Pivot, I think 2 I's. Yeah, so it's always the first in the row, the first one, and it has to have, if any numbers to the left, it must be 0. And you cannot have a pivot like under each, like they have to be to the right from the row above. That's what they mean with is always strictly to the right of the pivot of the row above. Okay, definition 2.6, row echelon form. A matrix is in row echelon form if all rows that contain only zeros and at the bottom of the matrix, correspondingly, all rows that contain at least one non-zero element are on the top of rows that contain only 0. Oh my god. But I guess that's what we already had before. Second point, looking at non-zero rows only. Okay, so the first one in our case. The first non-zero number from the left, also called the pivot of the leading coefficient, is always strictly to the right of the pivot of the row above. Yes, this is what we had here in red. Here in red. Okay, so next point, basic and free variables. The variables corresponding to the pivots in the row echelon form are called basic variables. And the other variables are free variables. Okay, we have basic and free variables. And the one which are associated with the pivots are the basic variables, and the other ones are free. Okay, so I guess it makes sense that we have different words for these variables because they must have different functions, right? For example, in 2.45, x1, 3, and 4 are basic. Okay, so we're talking about x, 1, 2, 3, 4, and 5. In these rows, we have always four versions of x1. Now, because x1 is here at least one time in the pivot, then we call it basic variable. So x1 is basic, x2 is basic, and x3 is basic, and everything else is free. The row echelon form makes our lives easier when we need to determine a particular solution. To do this, we express the right hand side of the equation using the pivot column, such that B equals the sum of the pivots. Okay, I'm not sure what they mean. So we have lambda 1, or basically lambda I. The lambda I are determined easiest if we start with the rightmost pivot column and work our way to the left. So here we have the solution 0, -2, 1, and 0. This is not the same. So we're still talking about finding a particular solution. And what they do is they sum up the pivots. We have 3 pivots, right? Row 1, 2, and 3. And what they do is they say, oh, I see. My problem was that I thought of rows, and what they're talking about are columns. So they say start with the rightmost pivot. I think this one. Then you have that one. And then you have that one. So they call this lambda 3. Or they scale it with that, I think. So if we go down here, you have -1, -1, 1, 0 for lambda 3. And here we have it the same. And then 1, 1, 0, 0, and 1, 0, 0, 0. Okay, good. They just add the columns. Let me think. Why? Where is B coming from? B is our particular. No, it's not our particular solution. It's 4-dimensional. Oh, I see. B is our B here. Because A is -1, it has to be 0. So 0, -2, 1, 0. 0, -2, 1, 0, same thing. Yeah, I think they're doing the same thing as what I described before, how to get to the particular solution. They just put the zeros there and then they just solve the equation. Okay, so given that, let's just keep going. We know that we can see here quite easily that lambda 3 has to be 1 because we have here this relationship. Okay, now we know that lambda 3 has to be 1 because no number for lambda 3 will make sense. Only 1 will make sense. Lambda 2 has to be -1. Why is that? Because if we take this equation, like this row, we know that we have something like lambda 2 plus -1 equals -2. So it has to be -1. And then the same is true for lambda 1. Okay, good. That makes sense. So in the end, we will have these one here, and the rest is 0 because they are free variables. And they say that they will set the coefficient implicity to 0. It's hard for me to like actually get the reasoning behind this. I know it must be like a systematic way. Or maybe it's mathematically the same as what I did before. I will just accept it that way. Okay, so let's go to the reduced echelon form. It's saying that it is reduced if it is already in the row echelon form. Every pivot is 1. and the pivot is the only non-zero entry in its column. Okay, in its column, that's the point. What about the normal echelon form? What was that again? So I think the normal one is just making sure that you're in a staircase. And also, they don't say that the pivot has to be 1. It was just assumption on my side, maybe in my head here. That in this case, we already have all the pivots are 1, but I don't see it here in that definition. Also, because we have the third point is the pivot is the only non-zero entry in the column. Here in our case, for the first column, that would be true. In the third column, it would be false. And the third one would be false too, because we have a pivot, which is 1, but there are also different entries, non-zero entries. Okay, so what they're saying now is the reduced echelon form will play an important role later in section 2.33 because it allows us to determine the general solution of a system of equation in a straightforward way. Okay, so remark, Gaussian elimination. Gaussian elimination is an algorithm that performs elementary transformation to bring a system of equation into reduced echelon form. Okay, so what Gaussian elimination is doing is it takes the systems of linear equations and brings it into this reduced echelon form, which is important for us so we can get the general solution in a straightforward way. Example 2.7. So how long is this chapter? Only this part. Okay. Example 2.7. Reduce echelon form. Verify that the following matrix is in reduced echelon form. The pivots are in bold. So maybe before we read that other part, let's just take a look at the matrix. We know that we have all the pivots, they have to be 1. That's right. Check. Check. Then we have the staircase form. Check. And they are always in a 0, right? The columns. Like in the columns where we have a pivot, that they are the only non-zero entry. Check. So I would say it is in reduced echelon form, but maybe we could check that again here, like the staircase way, or the normal echelon form is saying that all rows that contains only zeros are at the bottom of the matrix. Correspondingly, all rows that contains at least one non-zero element are on the top of the row that contains only zeros. Yes, yes, yes. The second part, looking at non-zero rows only. The first non-zero number from the left is always strictly to the right of the pivot. Yes, okay, so it's basically just a staircase form. So I would say yes, I could verify that it is in reduced row echelon form. So let's read the text. The key idea for finding a solution is to look at the non-pivot columns. Okay, the non-pivot columns. We have one here and one here, which we will need to express as a linear combination of the pivot columns. Yes. Okay. So a linear combination is somehow you try to express one vector as a combination of 2 vectors, for example, I think. Okay. The reduced echelon form makes this relatively straightforward, and we express the non-pivot columns in terms of sums and multiplies of the pivot column that are on the left. Okay, so we try to express the non-pivot columns with some kind of sums or multiplies of the pivot columns. The second column is 3 times the first column. Yes. We can ignore the pivot column of the right of the second column. Therefore, we obtain 0. Okay. I can say that do a times 3, then we have the second column, right? Do we need to do like a linear combination of the other ones too? I don't know. Yeah, the easy part is because of the pivot column, we only have one there. That we can just multiply. So we could multiply this one with 9 and minus 4 to get like the second non-pivot column. Okay, not sure. Let's read. So therefore we obtain 0. We need to subtract the second column from the from 3 times the first column. Okay, I'm not getting this. We already obtained 0. Okay, let's take a different color. So let's read again. The second column is 3 times the first column. Okay, that color is not good. The second column is 3 times the first column. Yes. So we just multiply the first one by 3, right? But they are saying we need to subtract the second column from the first. No, we need to subtract the second column from 3 times the first column. From 3 times the first column. So what they're saying is, okay, let's just give them here some names. They're saying we need to subtract the second column from 3 times the first column. Okay, I guess that makes sense. So, okay, now we look at the fifth column, which is our second non-pivot column. Yes, the fifth column can be expressed as 3 times the first, 9 times the second, and minus 4 times the third column, right? Yes. That's what we already had here in blue. We need to keep track of the indices of the pivot columns and translate this into 3 times the first column, 0 times the second column, and 9 times the third column. Oh, and minus 4 times the fourth column. I'm not understanding. I'm having a problem here. Okay, so we have already this matrix, which is in reduced echelon form. We have 3 pivot columns. Then we say the second column is, we need to subtract that. We need to subtract basically minus 3 times C1 to get 0, right? This is all to get 0. And the other one, how to get 0 is we take C4, then we subtract 3 times C1, then 9 times C3, and then minus 4 times C4. Actually, I think this has to be a plus, right? We have to add. Now I don't know what to do now. Okay, we can have these two equations, and then what? Well, I'm not really sure. Well, I can see the ratios here. You can see here that's a ratio of 1 and 3. Like, we can see that here. And here we have a 3 and oh, sorry, I've made here a mistake. This has to be 5. Yeah, so I can see all the ratios here. I'm not really sure what to do with these ratios. Also, the sign is flipped. Okay, let's try to read this again. I will read this again from the beginning. Sometimes you need more time. It's okay. Okay, let's do it again. 2.7, reduced row echelon form. Verify that the following matrix in reduced row echelon form. Okay, done. It is. The key idea for finding a solution is to look at the non-pivot columns, which we need to express as the linear combination of the pivot columns. Okay, so in the end, we are looking for a solution x, and we say x is actually lambda 1 plus lambda 2. And we know that it's only 2 lambdas because we have two non-pivot columns. So, okay, so they say the reduced row echelon form makes this relatively straightforward, and we express the non-pivot columns in terms of sums and multipliers of the pivot column that are on their left. Oh, I see. What they mean with on their left is we try to express this one by looking only with the pivots on the left, and we try to express this one by looking all of those pivots on the left. So we have C1. Let's use 2 different colors here. So let's define C1. C1 equals 3 times C1. C2 equals 3 times C1. And then we have C5, and that equals 3 times C1 and 9 times C2, no, C3, and minus 4 times C4. Now, because we want to have them 0, I think, right? We are moving C2 and C5 to the right side. Okay, sorry, my device just shut down. So I just wrote the equation again. And what we were about to do is we have those 2 equations here. Let's change the color. Blue and green. So okay, now this point is now important. Therefore, to obtain 0, we basically need to subtract those. We need to subtract the second column from 3 times the first column. So what they're doing is they're moving that part here and that part there, right? Okay, so I'm not really sure. We can have a solution where we have 0 equals like that, but we could also flip the signs, right? I mean, yes, I have no idea. Like, obviously we have here, we chose the first version, this one, but could we have just flipped all the signs? I guess we can flip it. Then we just have to flip also the signs of lambda, right? Okay, I don't know. I will just leave it like that. So basically what they're saying is for the first equation we're getting this one, and the second equation is doing that. I don't feel like I completely understood this part here. I mean, we are trying to express it as a linear combination. What we have done, we said column 2 is equals 3 times column 1. Okay, maybe we will build intuition later on this part, but at least we know how to do it, at least how to do the math, even if the intuition is missing a bit. Yeah, all right. I guess this is it for this part. Thank you for watching all the way through, even though it was a bit rough. Yeah, next time we're going to continue with the next chapter. All right.